Our first speaker in session 2 is Jonathan Julian Huerta Munive from the University of Sheffield, who will talk about differential Hoare logics and refinement calculi for hybrid systems with Isabelle/Hole. So please, the floor is yours.
Thank you. Thank you for allowing me to speak to you today. So I want to present joint work with Simon Forster from the University of York and my supervisor, Georg Struth. And basically, what we have done is a framework within the proof assistant Isabelle-Hole. And this framework has allowed us to derive two calculi for verification of hybrid system. One is, we call it a differential Hoare logic, and the other one, we call it a differential refinement calculus. So for hybrid system verifications, I brought an example. It's a fairly common example from the literature. So there's supposed to be a thermostat regulating the temperature in a room. And you want the temperature to be comfortable. And in order to guarantee that what the thermostat does, it takes some measurements. And after that, it takes a decision of whether to turn a heater on or off. Then, depending on the status of the heater, the laws of physics of the temperature in the room change. So, and the key thing to notice about all of this is that we can model mathematically each one of the entities of this system. So the physical laws, they are modeled with differential equations. The requirement that the temperature is comfortable can be modeled with a predicate with upper bounds and lower bounds for the temperature. And also, you know that the program is a mathematical entity. Now, the key insight that Andre Platzer had when he defined his differential dynamic logic is that you can sequentially compose the discrete program with the differential equations of the system, and you can wrap them inside a loop operation, so that basically you're saying that the system is evolving according to the differential equations, and every certain amount of time the discrete control intervenes to alter those dynamics. Whenever you combine discrete control with continuous dynamics, you get what is called a hybrid program. And the great thing about hybrid programs is that we can embed them in partial correctness specifications. So for example, in previous work with this framework that I want to describe to you, we have made it possible for Isabelle to encode hybrid programs inside forward box operators, so that we can guarantee that after the execution of this hybrid program, the thermostat will guarantee that the temperature is comfortable. Now, this framework in particular, well, I've said we have implemented it in Isabelle-Hole. And in previous work, we did it with model cleaning algebra. So the way we built it was that on the one hand, we had huge libraries from topology, analysis, and differential equations that have derivatives, limits, integrals. And on the other hand, we have the cleaning algebra libraries that work for verification of while programs. And then we just use the differential equations from the ODE libraries, and we plug them into the model cleaning algebra verification components, so that now they can reason about hybrid programs. And of course, because we have done it with model cleaning algebras, what we obtained there was forward and backward predicate transformers with box operators and diamond operators that allowed us to reason equationally with weakest liberal preconditions. And because of this, we had a high degree of automation. You know, the weakest liberal preconditions tackled the program structure recursively until we were just left with properties about real numbers and differential equations. And to tackle the differential equations, we had to add support, well, some procedures to study them. So for example, one procedure required that users supply the solution to the system of differential equations so that the verification goes through, and alternatively, if the users do not have the solution to the differential equation, they can reason with invariants. And of course, because everything is done shallowly in Isabelle-Hole, so everything is checked by the proof assistant. So the components that we end up with are correct by construction relative to the trust on Isabel. Now, this framework, because it's shallowly embedded, we can quickly expand it or refine it. And in particular, there's a clear observation that Hoare logic is enough for verification condition generation, and the related Morgan's refinement calculus also suffices for program construction. So there's a lot of extra information coming from forward operators, box operators, and diamond operators. So there's a natural question to ask if we can obtain within this framework variants of these calculi so that they can do hybrid program verification. And that's the main contribution of our work. With the framework that we had, we defined the differential Hoare logic, which is based on clean algebras with test, and the differential refinement calculus based on the refinement version of those algebras. And they consist just of a single extension to the rules of traditional Hoare logic and the refinement calculus. We did not stop at that. We also extended our framework because we wanted to add more modularity to it. So we used the algebraic entity of lenses so that we can reason about various store models, and to make the calculus flexible, we can also add invariant reasoning like differential dynamic logic does. And finally, we created some tactics that increased proof automation. Overall, the verification components are available in this online repository. And if you're not interested in downloading the tool, you can also download a proof document. And it's about 53 pages of proofs long. So it's a quite medium-sized formalization. Now, I'm going to talk to you about how this framework works and how it allows us to build verification components. And we need to start with an algebra. And for the case of the differential Hoare logic, we start with a clean algebra with test. And just remember that elements of the clean algebra represent programs. And in the additive monoid, addition represents non-deterministic choice. The multiplication represents sequential composition. And the identity of the additive monoid is the aborting program that stops the execution, and the unit of the multiplicative monoid is the skip program that does nothing. And of course, we also have the clean star that allows us to represent finite iterations. And we extend, to obtain the test, we just take a subset of the clean algebra that shares the operations of the clean algebra, and with these operations, it forms a Boolean algebra. Clean algebras with test already provide us with infrastructure to define traditional while programs like the if then else branching or the while loop. And they also provide partial correctness specifications in the form of Hoare triples. And the way we do this in Isabel is that they are formalized via type classes and inside these type classes, we can write the axioms of the clean algebra where we derive each of the consequences of the clean algebra, and we can define all of these entities. And then we can instantiate this type class to a specific type, which would correspond to the model of the clean algebra. And in this case, we instantiated the clean algebras with test to the model of state transformer instead of the standard relational semantics, where a state transformer is a function that takes an input state and gives you the set of all possible output states of the program. And the reason we did this was because there is a very natural state transformer from the dynamical system literature that we're going to see later on that fits nicely within this framework. And well, of course, you know that state transformers form clean algebra. So for example, here we have the sequential composition is modeled with the Kleisli composition from the power set monad. And finite iteration just recursively applies this Kleisli composition and obtains every finite state of the iteration by taking the union of all of them. And also we can model tests with state transformers. So the tests are true if they map to the singleton of the original input state, or false if they map to the empty set. Therefore, negation just swaps these values. And of course, the partial correctness specification is as you would expect. If we start in a state satisfying the precondition, then after the execution of the program, we will end in a state satisfying this post condition. Now, notice that we have remained agnostic to the type of the elements of the states. And we want to keep that so that we preserve the modularity of this approach. So in order to do that, we add lenses, which are an abstract algebraic structure that allows to manipulate the program store with an access and a mutation function. And their axiomatization is well known, and it goes back at least to Ralph Johann Bach or Joachim von Ritz. And the way we use them is that we use lenses to model the variables of the hybrid programs, so that the get function queries the value of the variable and the put function updates it. So that the axioms are really intuitive. They are just saying that if you query the value of the variable after updating it, then you get the value of the updated variable. If you update twice, then that's the same as just updating once, but with the second value of the update. And finally, if you update the state with its current value, then that's the same as doing nothing. So in order to obtain a state transformer semantics for assignments, we need a function that takes an input state and gives you the set of all possible output states. So for this input state, what we are going to do is map to the singleton of that very same state S, but updated to where the variable X is updated to the value of the right-hand side of the assignment. And we have also used lenses because, as we have seen before, there is this Isabel UTP project where Simon Foster and James Baxter, who is going to talk in the next talk, they have contributed a lot to it. So there's a lot of infrastructure to work with in the proof assistant. And at this point, what we get is the rules of traditional Hoare logic. So the first four are given by the Clini algebras, and thanks to the use of lenses, we now have the Hoare rule for assignments. But because we are all working with hybrid programs, we have also extended them with the rules for traditional hybrid programs of differential dynamic logic. Now, at this point, the only thing that we're missing is the differential equations. And we need a state transformer semantics for them. So for the state transformer semantics, what we do is that we can consider the differential equation as a vector field. So for example, suppose that the differential equation represent the movement of particles in a fluid. So then the solution to the vector field would correspond to each point in space. It assigns a direction and a velocity to the particle in the fluid. And then the solution to the differential equation would be a trajectory that the particle follows along the fluid that is always tangential to this vector field. To get the state transformer semantics, we take initial values. So instead of ODEs, we get initial value problems. And to each initial state S, we assign it the set of all possible points in the trajectory, which is the natural state transformer from the dynamical system literature called the orbit of the state. However, for verification of hybrid programs, people usually add some boundary conditions. So for example, if the fluid was inside a container, the boundary condition would be some kind of restriction on the movement of the particle. So we need to modify this state transformer to adapt these boundary conditions. The way we do it is that we have to take into account that initial value problems may have many solutions. So we define the set of all possible solutions to the initial value problem. And for each one of these solutions, we define the guarded orbit, which is exactly the same as the orbit as before, but with every initial segment protected with the boundary condition. We can take all these orbits together and for every one of these solutions, take the union so that we get a final state transformer for the differential equation, or as we call them, evolution comments. Now, whenever we satisfy Picard-Lindelof's theorem, we are guaranteed existence and uniqueness of solution, and that's a very common scenario in applications. And with the existence and uniqueness, this set on the right-hand side becomes just the single guarded orbit of the unique solution. And of course, we can also derive the inference rule for evolution commands, which says that in order to satisfy the post condition, we need to satisfy it along the trajectory of the solution, as well as the boundary condition for every initial segment. And at this point, we have already obtained all of the rules for differential Hoare logic. Now, but we want to extend it to do similar reasoning as differential dynamic logic. So we have defined invariants. So from Hoare logic, you know that an invariant for a program is a predicate that if it's the system starts in satisfying the predicate, then after the execution of the system, the predicate remains true. And in particular, for differential equations, there's a very interesting property that we have proven, that an invariant in the sense of Hoare logic for evolution commands is actually an invariant from the dynamical systems literature, where here what we're saying is that if the orbits start within the set defined by I, then the orbits will remain within that set. And because we have defined invariants and we have added properties that structurally and incrementally tackle how to prove that something is an invariant for the vector field, we can do weakening and strengthenings in order to show properties about invariants, as we usually do with while loops. Now I brought you a verification example in order to see how we do this process in applications. And for that, we need to finally settle for a store model. And in this case, I decided to use the set of functions from the finite set of 4 numbers to the real numbers. The get function just applies the function to the corresponding value, and the put function just updates it, so that we get temperature time, the measured temperature by the thermostat, and the variable that controls the heater. They are all correspond to one of the entities of the finite set. Now, for the differential equations, you can look here that Lenses provide us a nice syntax so that we can actually almost copy the differential equation written in LaTeX and use it as the defining equation in Isabelle Hall, where before we had to use some lambdas and notation that polluted our interaction. So Lenses provide us this nice syntax. And in order to prove that the thermostat behaves as we desire, we need to supply the solution to the differential equation. And again, notice here that we are using exponential or a transcendental function. And even though we do not have diamond operators like in differential dynamic logic, still we are able to express operations that traditional differential dynamic logic cannot do, because they are restricted to first order real arithmetic, while we have the higher order setting. Now, the procedure to verify the thermostat, we need to supply the solution, show that this indeed satisfies the conditions for Picard-Lindelof theorem, and then also show that this is in fact the solution to this differential equation. The formalization of the thermostat is just as we showed at the beginning. We have the boundary condition for the differential equation. We have the loop invariant, the control, the dynamics, and we loop them together as we did at the beginning. And in order to verify this hybrid program, notice how there's a medium size or relatively few interaction of the user. They just have to apply our tactic that blasts away the program structure. And before they of course, they need to prove the that the Picard-Lindelof theorem holds for the vector field, which is called in this second line. And also there's yet lack of automation in Isabelle-Hall for reasoning with real numbers. So we have to supply supporting lemmas in order to complete the proof automatically. Now for the differential refinement calculus, we just need to add a refinement operation to the clean algebras with tests, and this refinement operation will of a precondition and a postcondition will already satisfy the Hoare triple, and it would be the largest program that does so. Again, we formalize this in Isabelle-Hall, and we only need to prove the soundness of these rules in order to obtain the rules. And we can derive for both traditional while programs and the programs from differential dynamic logic. For assignments and evolution commands, notice that they correspond exactly to their corresponding Hoare triples. So for assignments, we need to satisfy the traditional refinement law, and for differential equations, we need to supply the solution to the initial value problem with the same condition, saying that the post condition should hold along the trajectory, and also the boundary condition should hold at every initial segment of the trajectory. To increase proof automation, we have added loss, monotonic loss and loss with invariants, just as before. And for an example, you can look at our papers, or if you want to see them later in the questions, I can show you a little bit how we do refinement with the components. So basically what I have shown to you is this framework that step by step builds a verification component. And in this case, we have derived the minimalist differential Hoare logic that verifies hybrid programs. And its related refinement, differential refinement calculus. We have added lenses so that they provide us a more algebraic management of the program store, and that also give us a nicer syntax for our verification examples. Also, lenses are very useful because the fact that we can change between program store, it means that we can now use possibly list for our verifications, and list in Isabelle have support for code generation, so that in the future we might have a code generation for verified executable code. Other lines of future research include the fact that, well, there's already support in Isabelle for total correctness of while programs, so we could analyze how we extend that to hybrid programs. And in particular, also differential dynamic logic has many extensions, and in this framework, because it's a shallow embedding, it's very easy to extend it and simulate the behavior of differential dynamic logic. And actually, in previous work, I have extended the libraries of formalized mathematics for Isabelle. And what this enables us is that it makes the components stronger and more capable of verifying more complicated structures. So in that previous work, I formalized linear systems so that certifications of unique solutions were not needed anymore, because I provided the general solution for all linear systems in the formalizations. And we can explore more variants of these differential equations, so differential algebraic equations or partial differential equations. And finally, all these procedures involve that the user needs to supply the solution or the invariant, and we would like to automate that with a computer algebra system, so that Isabelle only does the certification work. You can see all these formalizations in the repository or in the proof document. And thank you very much for listening. I'll listen to your questions.
Thank you, Jonathan. So please, if you wish to applaud, you can unmute yourself or use the applaud symbol. Yeah, applaud silently, but holding your hands in the air. Yes. So, any questions? So, Jonathan, I actually have a request, not a question. Could you put the link, which is on the bottom of your slide, into the chat? Because you can copy paste it into the chat, but we cannot copy paste from your slides.
Yeah, sure.
Exactly, like this. So I guess this is a general request to people giving presentations that any links they want us to use, they are better in the chat than in the slides. So, but I had a question too. Let me find it back. So I have some good French colleagues which are working on Zellus. Do you know Zellus or Zellus, as we call it in French?
No, I think the name does not ring a bell to me.
So that's a language for synchronous hybrid systems based on Lustre, another nice French language, which at least French people seem to think that it's a rather successful story, all the Lustre thing. So this is also a language for hybrid systems, and so I don't see why your work should not be applied to this. So this is been done at in Paris. What is he called? Marc Pouzet. He is doing those zealous things. So I think that so there might be something interesting there.
Yeah, can you repeat the name of that, please?
I can put a link in the chat. Aha.
Yeah. Also, I think well, I haven't been able to send the link to everybody. I sent it to you. If you can,
yes, I
share
can.
it with everybody, please. So yeah, what you mentioned. Well, I haven't taken a look at the semantics of the system that you mentioned, but because the approach is very flexible, yeah, potentially we could, but I want to be careful in saying that, in asserting that, because I do not know very well.
Yeah. Also, I mean, it's slightly different because it's got this synchronous model of time, right? So essentially, time is proceeding in lockstep. But I think this could be an interesting extension.
Yeah.
Okay.
Yeah, I think.
Any further questions? So if not, then yeah, if you wish, you can applaud the speaker again. I will do so.
Okay.
Thank you for your nice talk.